Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's class. In today's lecture, we will start discussing the applications of quantum mechanics. If you remember, in last several classes, we discussed the principles and postulates of quantum mechanics. Now, we have enough information so as to prepare ourselves to deal with some real systems. To begin with, we would actually look for quantum mechanical solutions for a few simple systems. These systems are exactly solvable, and the first one that we will be dealing with is this very famous so called particle in a box problem. Before we discuss the quantum mechanical solution of the particle in a box, let us discuss about its chemical significance, because often what happens is that students get confused with the terminology. What is this particle and what kind of box is it? Let us put the matter straight at the outset. Do not imagine any classical box like the picture shown here or any particle inside it. So, this classical picture should be removed from your mind. I will now try to tell you that what chemical systems we have in mind when we call particle in a box. We know from atomic structure that an atom composed of a central nucleus and one or many electrons going around it. Now, the electrons are under the influence of the nucleus. So, the electrons are bound by a box that the nucleus creates. So, an atom is essentially represents particle in a box, where the particle is an electron and the box is the nuclear field that the atom produces. Now, similarly, when we go beyond an atom to a molecule, for example, let us try to draw a few simple molecules. For example, the most simplest of them, let us consider water. For example, in water we see that there are 10 electrons, 8 electrons from oxygen, 1 each from each hydrogen, and there are 3 nuclei. These 10 electrons are restricted to the nuclear field that this water molecule produces. So, the electrons are somewhere here in this region of space, but certainly they are not here, far away from the nucleus. If you imagine conjugated diene, 1,3-butadiene, or its extended version, the hexatriene, in this case what you see is that there are these pi electrons which are essentially delocalized over the entire chain of the molecules. So, these pi electrons are all over this molecule. So, their electron distribution can be shown to move around this one dimensional box. Similarly, if you imagine your benzene molecule, we know that we have got 6 pi electrons, and these pi electrons are again delocalized over the benzene ring. So, in this case the particles are restricted in this box, in this case the particle or the electrons are restricted in this box, and here in case of benzene they are restricted in this box. You can see that from one molecule to another molecule, the shape, the size, the dimension of this box changes, but the bottom line is the same, that we have some particles, by that I mean electrons, trapped in the nuclear environment. So, this is what we mean when we say particle in a box. All right. Now, we will are now after this point, we would now look at how to solve this system quantum mechanically. So, when we say that we want to solve this problem quantum mechanically, we of course have Schrodinger equation in mind. We already know that everything that we need to know about a system is out there in the wave function, and the wave function psi has got all the information in it. But this information can be extracted from the system by applying an operator. So, the operator is Hamiltonian operator, which corresponds to energy. When we apply Hamiltonian operator and this wave function which contains all the information, we get the observable corresponding to this operator. So, since we are applying Hamiltonian operator, we are going to get the observable energy, and this is the Schrodinger equation that we already have seen. What is Hamiltonian in here? Hamiltonian has two parts, it is an energy operator. So, when I have a particle or an electron in a molecule, so I have kinetic energy of that electron and the potential energy of the electron. So, the kinetic energy operator, we have already seen that the kinetic energy operator has this kind of form, which is minus h bar square by 2 m, and the second derivative with respect to all three Cartesian coordinates x, y and z. So, in this case it says that the electron can actually travel in along x direction, y direction, z direction, and the particle or the electron has a mass of m. If a particle has a mass of m and it is allowed to move in all three directions, this is the kinetic energy operator for that particle. But in today's class, we will restrict our discussion to a simpler system, that is, instead of looking at the particle's movement in all three directions, we will restrict the particle to move only along one direction, and that is along x direction. So, that would actually simplify our kinetic energy operator. So, you see this particular formulation had both x, y and z, but in this case, since I am restricting my movement to only x direction, the kinetic energy operator has only d square by dx square, and you also should notice that I have moved from partial derivative over here to simple derivative, normal derivative in this case, because now I have only one dimension. I have ignored y and z because my particle is moving essentially from minus infinity in x direction to plus infinity in x direction, and this is my origin. So, this is about the kinetic energy. Now, what about the potential energy? So, what I see here is that this is the x axis, my molecule is somewhere here. So, the electron will be restricted within this field. So, what I have done is now I am putting my molecular environment between 0, x value of 0 to x value of L. What the shaded region shows is that here in this case the particle experiences huge amount of potential, whereas within this region the particle experiences no external potential. That means the particle is free to move within this region. So, from this diagram you should imagine that my molecule is kept somewhere between x equals 0 to x equals L. So, that is why the particle is allowed to move within this molecular environment. It is never going to be found far away from the molecular environment or the nuclear influence of the molecule. So, when I define my potential energy like this, I can very well express that in terms of an equation. So, V, the potential energy operator, is 0 when x is between 0 and L. So, within this region, and V is infinite elsewhere. So, 0 to minus infinite and L to plus infinite, V is infinite, or the potential energy is infinite. Now, we have defined now three different regions, region 1, region 3, which experiences V equals infinite, and region 2 where V is 0. Now, I would solve the quantum mechanical problem in each of these regions. We would begin with regions 1 and 3. So, here we would write down the Schrodinger equation H psi equals E psi, where the kinetic energy is given by so this is T psi plus V psi, which V, the potential energy is infinite, which gives me E psi. So, this is the Schrodinger equation in regions 1 or region 3, because in both cases this is my potential energy operator. If I want to solve this, I can take this second term to the right hand side. So, it will become E minus infinite, which will be minus infinite, and then I can simplify this solution by writing down I just took this h bar square by 2 m to the other side and multiply anything with infinite, it remains infinite. So, I have this simple differential equation, but I see that in the right hand side I have wave function multiplied by infinite. So, therefore, if I write down the wave function, I would have to have this. So, wave function is simply 0 in region 1 and region 3. So, region 1 wave function is 0, region 3 the wave function is 0. Does it make sense? Yes, because we know the wave function itself does not have physical interpretation, but what has physical interpretation is psi star psi, the wave function multiplied by its complex conjugate. When you do that, what is what do you get here? Again you get 0, and what does that probability density tell? That the probability density of finding the probability of finding the particle in region 1 and region 3 is 0. Does that make sense? Of course it does, because we have modeled our system where within the molecular environment or within the box there is no potential energy, but the moment the particle wants to go out of the box, it experiences huge amount of potential energy that it has to climb, and it can never climb because we have kept our V as infinite. So, therefore, the particle never escapes and we have probability 0 outside the box. So, this makes sense. Now, we learnt about the region 1 and 2, region 1 and 3. Now, we would go actually to the next solution, that is in region 2. In region 2, again we will start with the same way, the way we started in region 1 and 3. So, we would write down the Schrodinger equation. But in this case the V potential energy is 0. So, V equals 0, and this is my Schrodinger equation. The wave function is written here. So, this is my V like last time. When I simplify this equation, I have you would be able to identify this equation from your mathematics classes. This is a second order homogeneous differential equation whose solution is well known. We are not going to get the solution, rather we are going to use the solution that we know from our mathematics knowledge and apply it in our course. So, for such an equation, the solution, the general solution is an exponential function. We call it e to the power alpha x. So, where x is my x axis, the dimension here, alpha is something that I do not know. I will have to find out this alpha for the given problem. When I apply this e to the power alpha x in this equation, you see the first term requires me to differentiate this wave function psi twice with respect to x. I know when I differentiate e to the power alpha x with respect to x, I get alpha into e to the power alpha x. So, if I do this differentiation twice, I would get alpha square e to the power alpha x plus the second term is simply a multiplication of the wave function. So, I have 2 m e h bar square e to the power alpha x, which is 0. Now, in each of the term in the left hand side we have e to the power alpha x. Since this is actually the wave function, we can assume that this is not going to be 0 and find the non-trivial solution from this equation as alpha square equals minus 2 m e h bar square, or in other words alpha would become, so square root of minus 1 will give me an imaginary root, the square root of these quantities would give me a plus minus So, I have a term like this. So, since this is rather a big term, so I am just giving it a short name I beta. I am calling this square root of 2 m e divided by h bar as beta. This is just for simplification in the notation. So, now what I have is that I wanted a solution for alpha, but what I have got now, there are two possible values of alpha, one is I beta, another is minus I beta. So, I write down, so psi is e to the power I beta x or e to the power minus I beta x. I one of these two solutions are each of these solutions is accepted. So, therefore, I do not know what more to do. So, therefore, I will accept both the solutions, but what I would do is that I would take a linear combination of them by giving a coefficient C 1 to this, C 2 to this. What do I do? What do I gain by this? I am telling that each of the solution is acceptable. So, therefore, I am giving some coefficient C 1 and C 2, and I would find out the coefficient C 1 and C 2. They essentially represent what is the contribution of e to the power I beta x, or what is the contribution of e to the power minus I beta x to the final wave function. This C 1 and C 2 have to be determined. So, I would just do a few simple steps of algebra. I will express this exponential function in terms of cosine and sine function. So, I have cosine of beta x plus I sine of beta x plus C 2, I have cosine of beta x minus I sine beta x. I can take the real quantities and the imaginary quantities separately. So, I have C 1 plus C 2 cosine beta x plus I C 1 minus C 2 sine beta x. I have got two new constants C 1 plus 2, C 1 minus 2. So, I will rewrite this as A cos beta x plus B sine beta x. Now, I have got a formula for my wave function A cos beta x, B sine beta x, where beta has been defined as square root of 2 a me divided by h bar, and A and B are the constants or the coefficients that I still do not know, and I would be spending time in learning about this. So, this is the wave function, the form of the wave function that I am getting from this exercise. We will continue our exercise further, but before that let us see what we have got. We have region 1 where the wave function is 0, region 2 where the wave function is 0, and region 1 and region 3 the wave function is 0, and in region 2 we have this wave function. Now, we already know that for a quantum mechanical solution, the acceptable wave function must be continuous throughout this dimension. From minus infinity to plus infinity, the wave function must be continuous. So, this gives us some additional boundary conditions that we would deal with. Okay. So, we have now the wave function for the region 2 as A cosine beta x plus B sine beta x. Now, we have to see that the wave function is continuous in throughout the region. So, at x equals 0, the wave function at region 1 and region 2 should be same. So, at x equals 0, psi 1 should be equal to psi 2, but we know psi 1 is 0 throughout. So, this is 0, and psi 2 for x equals 0, this equation is simply beta x plus B sine beta x. So, I know that when x is 0, sine function is 0, when x is 0, cosine function is 1. So, therefore, the right hand side is simply A, but I see for boundary condition to make the wave function continuous at x equals 0, I must have A as 0. So, the solution that I got in the region 2 which has A and B at the two coefficients for cosine function and sine function, I see that the boundary condition requires me that the coefficient for the cosine function must vanish. So, therefore, the wave function that I am left with is simply B sine beta x. Now, I will look at now x equals L at this region. What happens to this region? In this region, psi 3 and psi 2 are operative. So, at x equals L, psi 2 should be equal to psi 3, but we know psi 3 is 0 throughout. So, therefore, B sine beta L, which is this here I used x as L, b sin beta L is 0. So, we know when this sine function becomes 0. So, the solution of that is that beta L should be n pi, where n is 0 or 1, 2 and so on. So, in this case I have already some idea about beta, that I see beta is n pi by L, and therefore, the wave function that I am looking for is b sin n pi x by L. So, I got a form of the wave function as this. So, you can see this wave function psi 2 wave function in the region 2 has a the functional form of a sine function, which depends on the L, the length of the box, pi a constant, x the variable, the dimension of the problem, and n is an integer which goes from 0, 1 to so on and so forth. So, therefore, the wave functions show that they are quantized. Not every sine function is a wave function, rather some specific discrete sine functions are the wave function or are the eigenfunctions of this system. What about the energy? We will start with this equation, beta L equals n pi, but we already know beta is 2 me by h bar equals n pi by L. When I solve this for E, I would get this E equals n square h square by 8 m L square. Again, let us look at the energy expression. Energy depends on the length of the box, that makes sense. Energy depends on the mass of the particle. Energy depends on the h, which is actually a universal constant, the Planck's constant, but energy also depends on another variable n, which can go from 0, 1, 2, 3, so on and so forth. So, therefore, since I have so many energy levels, to identify them, I am calling E this, giving an index to this energy, I am calling this E n, because E will depend on n. Now, there is one more point to look at about the possible values of n equals 0, 1, 2. When we have n equals 0, when you look at this wave function b sin n pi x by L. So, when n is 0, this quantity becomes 0, does not matter what value of x you put here, the wave function is always 0. We already knew that wave function has to become 0 in region 1 and region 3. Now, we say that if n is 0, then the wave function is also 0 throughout the region between x between 0 and L. So, that means if n is 0, the wave function is 0 all along. If wave function is 0, its probability density is 0 throughout. So, that means there is no particle, and that is a trivial solution, and that solution is not acceptable. And what we say is that this n equals 0 condition we are excluding. So, therefore, allowed values of n are n equals 1, 2, 3 and so on and so forth. Now, we have got the functional form of energy, we have got the form of the wave function. Only one thing that is unknown is what is this b, the constant b, that we do not know, and we can find that when there is a wave function which has only one unknown. We have to remember that the wave function has to be normalized. When we normalize this wave function, this coefficient can be determined. So, this is what we are going to do next. So, now we are going to normalize this wave function. When we say we want to normalize the wave function, we have essentially we say that psi star psi dx between minus x goes from minus infinity to plus infinity should become 1. So, this is the probability density at any point psi star psi dx is the probability within a interval of dx, and when we integrate from minus infinity to plus infinity. So, that means we are calculating the probability in the entire range, and that has to become 0. So, we can break it down to minus infinity to 0, the second term 0 to L, the third term as L2 plus infinite should be 1. But we know between L to infinite the wave function is 0, between minus infinite to 0 the wave function is 0, only this region is finite. So, we will look at this, but we already know psi is b. So, psi star will have a b square term. So, 0 L and I have a sine square n pi x divided by L dx, and we have to evaluate this integral. We can express it in terms of a 1 minus cosine divided by 2, that the integration limit is 0 to L. So, here I see that the first term will have 1 by 2 dx. So, which will give me L by 2 minus the second term will have a integration of cosine function, which will give me a sine function. And this is between 0 to L. When I look at this second term, when x is equals to L, the function is sine 2 n pi, so which is 0. When x is 0, then this function is sine 0. So, therefore, the second term when I evaluate the two limits, it will give me 0, this vanishes. So, therefore, I am left with only b square into L by 2, which is equal to 1, because this is what we wanted to do. Now, when I use the value of b, I solve this, I get the value of b is this. So, therefore, the normalization constant what I get is 2 by L, and I can write down the wave function now. And you see that this psi depends on n. So, I am writing down this psi n. If few things that you should, I am just for the sake of completeness, I am writing down the energy expression, which you will see again. What we see is that the wave function has n dependence, the energy has n dependence. So, both wave functions and the energies are quantized, and that they have explicit dependence on n. Another thing to remember is that the normalization constant that we determine, which is 2 by L, it does not have any n dependence. So, it does not matter which eigenfunction we are talking about, the normalization function remains the same. So, to summarize, in today's lecture we started with defining what is particle in a box problem is, and then we try to do quantum mechanical solution for this. We formulated the Hamiltonian, the kinetic energy operator, the potential energy operator. We solved the system in 3 regions. We saw that region 1 and region 3, where the particle experiences infinite potential, the wave function vanishes and the wave function remains finite only within the box 0 to L. In today's lecture, we will continue our discussion. Thank you for your attention.